Section 3.8, Curve Sketching. The objectives of the section are to define when a function is decreasing or increasing on an interval, analyze the first derivative to determine the intervals on which a function is increasing or decreasing, and find the locations of the relative extremas, and finally analyze the second derivative to determine the intervals on which a function is concave up or down, and locate the points of inflection. So we begin with the definition of increasing and decreasing. So what does it mean to say that a function is increasing or decreasing on an interval from a to b? So supposing that the f function is continuous on a closed interval from a to b and differentiable on the open interval from a to b, then we say that the f of x function is increasing on the interval a to b if the derivative f prime is greater than 0 on all the x coordinates or the x values inside the intervals a to b. And we say that the function is decreasing on a to b open when the derivative f prime of x is less than 0 on all the x's inside the interval a to b. And finally, if the function's derivative happens to be equal to 0, so if f prime is equal to 0, then we say that the function is constant. So it's neither increasing nor decreasing on that interval. So with that in mind, if we look at this graph that's provided here, we can see that the function f of x that's drawn in this picture is increasing on the interval from a to c2, because on that interval the function is going up, and it's decreasing from c2 to c3. So that's the second interval there. That's the function decreasing, and then it increases again, and finally this function that's provided decreases on the last interval. So as you can see, when the function is increasing, the slopes of the tangent lines are pointing up. So therefore, the derivative is going to be positive, and that's why we said that the function is increasing. And when the function is decreasing, the tangent lines are going to be pointing sort of down. So that's what makes the function decrease, and that's how we describe it. Something that we can see quite obviously on this graph is that when the function changes from increasing to decreasing or decreasing to increasing, we get what's called a maximum or a minimum. So that happens when the function goes from increasing to decreasing or decreasing to increasing. We need to know that because in the next few pages, we're going to be interested in finding the extremas, meaning the maximum and the minimum of the function. And so keep in mind that when the function goes from increasing to decreasing, then you have a maximum, and when it goes from decreasing to increasing, it's going to have a minimum. Now, if the function does not change before and after a point, so if it's increasing before and after a point, then that point is not going to be an extreme. So we have a couple of those examples on this graph where the function was increasing before a point and increasing afterwards, and so that point itself is not a maximum nor a minimum. So what we described just right now is called the first derivative test, and it's this theorem that says that if f prime of x changes from positive to negative at a point c, then the function f has a relative maximum at x equal to c, and vice versa. If f prime changes from negative to positive at a point c, then the function has a relative minimum at the point c. So we're going to be basically drawing a number line, and we're going to do some testing to determine if the function is increasing or decreasing. And so if you see a plus on the test, then a minus, you'll know that you're dealing with a maximum point in between. And on the same other hand, if you have a decreasing, then an increasing function, then you'll know that the point in the middle is going to represent a minimum value for the function. So these values C that we see on these little graphs, so this point C here and this point C there, those are going to be the critical values of the function. And remember how you find the critical values. You just find the derivative and you set it equal to 0. You find what makes it undefined, and that gives you the critical values. And what we are doing here is going to be called the first derivative test, and we're going to illustrate that with some examples. Now, in this section, we are interested in finding the maximas and minimas of a function, and typically we're not going to be given a domain or an interval that they care about. So we're going to assume that the function is defined on the domain and figure out what the domain is if it's not provided, and then test whether it has a maximum or minimum on that whole domain. In the previous sections, we were given an example with a closed interval, and you're interested in finding the absolute max and the absolute minimum. here the question is going to be just to find the extremum, meaning the max and the minimum, and typically you're not going to be provided with an interval. So you have to assume that the function's interval is the domain. And that's the major difference between this section and the previous ones. So in example number 1, we are given a function f of x, which is 3x squared minus 4x minus 8. And as you can see, this function here is an example of what's known as a quadratic or a polynomial. And polynomials are basically functions whose domain is all real numbers. So this is the interval that we want to find maximas, minimas, and so on and so forth on. Since there's no interval listed in the problem, we will assume that whatever question they ask us is on the interval from negative infinity to positive infinity. This is an assumption that we have to make whenever the interval is not provided. Because if they wanted me to find the maximum or minimum on a specific domain, then they would provide the interval for me. So in part number 1 of this question, it says find the critical values of the function f of x. And so to find the critical values is the same standard procedure that we did before. We're going to find the derivative and figure out what makes it equal to 0, what makes it undefined. In this case, the derivative of 3x squared is going to be just simply 6x. The derivative of 4x is going to be 4, and the derivative of negative 8 is going to be 0, which we typically don't write, and so the answer is just 6x minus 4. Now, this is again a polynomial. It's a linear function because the x has power 1. So we are going to need to figure out what makes it equal to 0 and what makes it undefined. Obviously, there's no values that will make it undefined because it's not a rational expression. There's no ln in there. There's no radical or anything. So this function does not have any values that would make it undefined. However, the derivative can be possibly equal to 0, and that would require x to be equal to 2/3. You can see there, you just need to isolate the x by itself by moving the 4 and dividing by 6 to get that x is equal to 2/3. And that's what we consider to be our critical value. So now the question in part 2 is to do a number line test and figure out the function's intervals of increase and decrease. So what do we do? So we draw the real number line and we drop x equal to 2/3 right in the middle of the number line. Notice how the number line starts at negative infinity and ends at positive infinity. Those are the same values found in my domain. And the 2/3 is the critical value that I found in part number 1. So if I had multiple critical values, I would list them in order from smallest to largest. In this case, I only have one of them, so that's why there's only one value in the middle. And to perform the test to figure out where the maximas and minimas are, or figure out where the interval of increase and decrease are, what we need to do is pick some test values. So these test values that we're choosing are completely random numbers that come before 2/3 and after 2/3. So just any number in the universe works as long as the number is after 2/3. In this case, I chose the number 1, but it could have been 10 or 15 or whatever. And in this case, I chose negative 10, but it could have been 0 or negative 1 or negative 100. It's up to you. You can pick any value you want. So what do you do with this test value? You grab it and you plug it into the derivative. So for example, in this case, what would happen if I plugged in negative 10 into my derivative? Well, I would get 6 times negative 10 minus 4, which would be negative 60, minus 4, which would be a negative 64 ultimately. And the answer is going to be negative. This is the only thing that I care about. This is why you're seeing a negative being placed underneath the line, to just remind me that the answer I got was a negative amount. Now remember, it shouldn't matter which number I pick, so let's pretend for a second I chose a different value. Let's say you decided that you don't like negative 10 and you prefer instead a 0, for example. 0 is a number before 2/3, so it should, in theory, work. And so let's find out. You're going to take the 0 and you're going to plug it into the derivative. So you're going to get 6 times 0 minus 4, which is 0 minus 4, which is again a negative 4. So again, the only thing that matters in this particular instant is whether the answer is positive or negative. And you can see again that regardless, the answer is going to continue to stay negative. So 0, negative 10, doesn't matter what test value you pick as long as it's before 2/3. And same thing again with a number after 2/3. So pick a test value. In this case, I picked 1. And so let's see what happens. You take the 1 and you put it into the derivative. So when you plug 1 into the derivative, you're going to get 6 times 1 minus 4, which is 6 minus 4, which is a 2, but that's in reality a positive 2. So again, the answer turned out to be positive, and that's the only thing we record on the test itself. We don't care about the 2 itself because remember, the 1 for the test value you chose is random. It was the only requirement is that it's bigger than 2/3. And so again, what if you decided to go with a different number? Let's say you decided to go with 10, for instance. So instead of the 1, you chose 10, for example. What would happen is you would get f prime of 10, which would be 6 times 10 minus 4, which is 60 minus 4, which is 56, and that's a positive value again. And notice how it is positive, and that's the only thing that counts. That's the only thing that goes on the test itself. So again, this confirms that it doesn't really matter which test value you pick, as long as the test value chosen is a number bigger than or equal to your critical value. Now, because there's a minus sign on the first half of the interval, we will say in specific notation, f is decreasing. So we write f with a little arrow going down. This notation indicates that the function is decreasing. And because the plus sign shows up on the second half of this interval, we will write f increasing. So notice how we do the test with the derivative, but the derivative tells us information about the function itself. And so on the interval from negative infinity to 2/3, it seems that the function f is decreasing. However, on the interval from 2/3 to infinity, it seems that the function is increasing. And that's what we will record underneath to provide as the final answer. So the final answer is provided in words with f of x is decreasing on the interval from negative infinity to 2/3. And remember again, this negative infinity and this positive infinity are the same values that you found when you looked for the domain. Now, the next part of the problem asks us to find the ordered pairs, meaning the x and y coordinates, of the places where there's a maximum or a minimum. And so just because we did this, we can already answer problem number 3, which is, well, what's the maximum, what's the min? And we notice in the graph that the function decreases, so it's going down for a while, and then it increases after, so it's going up after. So when your function goes down for a while, then it goes up for a while, that creates a low value. And so that will be what's considered in math as a minimum. And so we will say that the f of x function has a minimum at x equals to 2/3. And how do we find the minimal value of the function? Well, we plug 2/3 into the original function f of x. This is how you find the y value always. So be careful. You need to use the original function, not the derivative. So the derivative tells you the x coordinate, but to get the y coordinate, you always go back to the original function itself. And in this case, a simple calculation, you can do this with your calculator or by hand. It's up to you, whatever you want. You'll see that the y coordinate is negative 28/3. And we can say that the function f of x has no maximum because on the number line that we drew here, we didn't have a spot where we had a plus sign followed by a minus sign. We didn't have a place where the function went up, then it went down after, creating a small hill. So there is no maximum on this graph. Then, oh well, not every function is going to have a maximum and a minimum. And so you can see the graph here on this part of the problem with the minimum shown, but how do I get this graph? So let's talk about that next. Let's turn on our calculator and see how we can reproduce this graph and then copy it to our paper. So as we do with every other problem, we're going to turn on the calculator, then go to the y and type in the equation, which is in this case 3x squared minus 4x and minus an 8. So that's the parabola that's provided. And we are just going to modify the window slightly to match what is on the paper so that when we are copying it to paper, it's going to be a little bit easier. On the paper, it seemed that the x-axis value started at -3 and it ended at around 5. So we'll put those numbers in. And the y coordinates, it seems like they went from -9 all the way up to +9, let's say. So you know what? I'm going to put -10 and +10 just to get a little bit more space. And finally, just click graph and you'll see the parabola appears on your screen. So next, what I want you to do is click on trace. And the first thing we're going to do is trace 2/3. This is the point in theory where we had a minimum. And as you can see, it is the lowest point on the parabola. This is also known as the vertex of the parabola. In algebra, you had different ways of finding the vertex. Well, now you have new methods, which involve finding the derivative and then figuring out the maximum and minimum. So this is a lot better because it doesn't rely on memorizing a formula. It's a little bit more intuitive. But that's the one point on the graph. And if you need more points to plot this to your paper, then you could just click on trace and trace randomly some x value. So for example, 0 gives me -8. If I trace -1, I get another value. Y is equal to -1. If I trace -2, the y is going to be 12, and so on and so forth. So you could do this again on the positive side, for instance. 2 gives us -4. If I trace 3, for instance, I get 7. And once you've collected enough points that you feel confident you can copy the graph, then you can just bring it over to the paper. And notice how I'm passing it through the point where y is equal to -8 there, and a couple of places where it crosses the x-axis. We can estimate those randomly, or we can just kind of eyeball it by looking at the graph for now. Remember, we are asking for a sketch of the graph, so it doesn't have to be super perfect. It just has to kind of look like a parabola that you see on the screen. Okay, so now that we looked at a simple example, let's take a look at a more complicated example where the h of x function is equal to x ln of x. And in this example, the very first part of the problem asks me to find the domain. But in general, whether they ask for the domain or not, it's a good practice for you to start thinking about the domain of functions. This will be especially true when we start dealing with rational functions, which is what's going to happen in the next section. So whether they ask this question or not, you should always try to answer that yourself, at least on the side or in your head, and just keep in mind that the answers that you get for the domain are relevant in all the problems. So in this problem, h of x is represented with x multiplied by ln of x, even though there's no multiplication sign. I'm going to mention it here because it will be useful later on when I find the derivative. And so the special thing about the natural log function is that we know the argument, the x that goes there, cannot be negative and cannot be 0. So this x has to be greater than 0, which implies that the domain of the function will be from 0 all the way to infinity. That is the domain. And so if I need to answer any questions about this problem, I'm only interested in what's going on between 0 and infinity. So if I see any critical values outside of this interval, I'm not going to pay attention to them. Okay, speaking of that, let's take a look at problem number 2, or example number 2, part 2, which is to find the location of any relative maximums or minimas. And they want us to confirm with our calculator. So the very first thing I need to do here is find the derivative, and this is the standard procedure pretty much in all the problems that we're going to be working on for a while. So if you don't really know what to do, just find the derivative and you'll be halfway done with the problem, because as soon as you find the derivative, you'll need to find the critical numbers, and that usually answers pretty much 90% of the questions we're trying to answer. In this problem, the derivative requires the product rule. So to find the derivative, I'm going to have to use the product rule, and I'm going to set it up with the f and g as usual, where f is the first term in the product and g is the second term in the product. And on the other column, I'm going to put the f prime and g prime like I always do, where the derivatives of f and g are here. So derivative of x is going to be 1, and derivative ln of x is going to be 1 over x, as we said in the previous section. The product rule requires me to multiply f prime g and then add the product of g prime and f. So when I do the product rule, don't forget there's a plus sign that appears because of the product rule. So to summarize, h prime of x is the product of these two corners, and 1 times ln of x is just simply going to be ln of x. And we have the plus sign from the product rule. And next we have to multiply the opposite two corners, the 1 over x, with the x. And I'm just going to multiply in my head. 1 over x times x is just going to be equal to 1. Now, once I found the derivative, the next thing I need to do is ask myself what makes the derivative equal to 0, or what makes it undefined. So what makes the h prime of x undefined in this problem? Now, to figure out what makes h of x equal to 0, I need to figure out what makes ln of x plus 1 equal to 0, because that's the derivative. That requires isolating the natural log, so we're going to have ln of x equal to -1, and then we need to involve the exponential e, because e will undo the ln of x, and so we get x equals to e to the -1, which is the same thing as saying 1 over e if you prefer to have a positive exponent. And given the nature of the derivative, ln of x plus 1, the domain of this derivative is the same as the domain of the original function, so we don't get any additional values in the second column where the question is what makes the derivative undefined. So we only have one critical number in this problem, and it's 1 over e. Okay, so now that we found the critical number, the next thing we're going to do is draw the number line that represents the domain. So in this problem, the domain was from 0 to infinity. And we're going to write h prime test on the side to remind us that this is the derivative test, the first derivative test. Later on, we will be doing something similar for the second derivative. So we want to be able to distinguish which one is which. That's why we're writing h prime of test on the side. The only critical number that I see in my problem is the 1 over e, so I'm just going to put it somewhere in the middle. This is the 1 over e value, and roughly speaking, this is about 0.3. Because remember, e is 2.7 roughly speaking. So now that we found the critical number and we've plotted the number on the number line, we need a test value before and a test value after. So I want you to pick a number that is smaller than 1 over e but bigger than 0. It has to be from the interval. So a good number might be something like 0.1, and I need another test value between 1 over e and infinity. There's plenty of numbers to pick from. I'm going to pick the number 10 just because that's my preference. So remember, the only requirement is that the number has to be from the interval, meaning between 1 over e and infinity, and any number should work. Now, what we do with these numbers is we put them into the derivative. Remember, the derivative is h prime of x equal to ln of x plus 1. So what we're going to do is put the 0.1 into the ln of x and the 10 into the ln of x and add the 1 at the end and see if the answer turns out to be positive or negative. So, for instance, if I plug in the 0.1 into my derivative, I would end up with ln of 0.1 plus 1. And I have no way to determine what this answer is going to be, whether it's going to be positive or negative, so I'll use my calculator and I'll do that in a second. Let me write the second one. H prime of 10 is going to be ln of 10 plus 1. And so, again, we will use the calculator to figure out what these values have to be. On my main screen of the calculator, I'll type in the ln of 0.1, close the parentheses, and hit plus 1. And as you can see, the answer is going to be a negative amount. So we know that the first solution that we're dealing with is a negative value. So what I'm going to do is record a minus sign underneath the axis right there because the answer turned out to be negative. And I'm going to write h with a small arrow pointing down. This reminds me that on this interval from 0 to 1 over e, the function h of x was decreasing. So you can write the whole word that h of x is decreasing, or you could just put the little h with the down arrow to remind you of that. Similarly, we'll do the 10 part, so ln of 10, close parentheses, plus 1, and you can see the answer is 3.3 roughly. And what matters is that the answer here was positive. So for the second test that we did, the answer turned out to be positive. So I'm going to grab that and again write it down underneath the interval to remind myself that the answer I got was positive on this interval. So what that means is that the function h was increasing. So remember, I got the number 1 over e from the derivative, and I do the test in the derivative, but it's the function itself that is increasing or decreasing on these intervals. So on one interval, the function was decreasing. That's the first interval, and we did that by testing 0.1, but you could have tested anything else. You could have tested 0.015, you could have tested 0.2. Anything between 0 and 1 over e would result in the same answer, which is a negative solution. So now that we've done all this, we can finally decide the intervals on which the function is increasing and decreasing. We can also finally decide the maximum and minimum. As a matter of fact, in this problem, it seems that the function went down and it hit the critical number, then it went back up. We are seeing that because of the minuses and the pluses on this number line. So by going down and then going up, we've created a small valley. So this guy is now a minimum of the function. And since I'm not seeing a plus sign on the line followed by a minus sign anywhere, that means there is no maximum on this function h of x. So let's record that in words. So first of all, h of x is decreasing on the interval from 0 to 1 over e. and it increases, and the function is increasing on the interval from 1 over e all the way to infinity. The h of x function has a minimum at the place where x is equal to 1 over e. And if we want to find the value of this, we will just plug 1 over e into the original problem. So if I want to know what the value is, so I'm going to write with value, and I'll just plug the 1 over e number that I got from my critical number. I'll plug it into the regular function. Sorry, it's an h of e. So if I plug it into the original function, I would get 1 over e multiplied by ln of 1 over e. And by the way, 1 over e times 1 over ln of 1 over e is really negative 1 over e. You can use your calculator or any other algebra skills to figure that out. So this is the value of the minimum. And we can confirm that in a second with our TI calculator. And the last thing we're going to write is that h of x has no maximum values. There is no place where the function is highest. So let's confirm all this with our TI calculator, which requires us to put basically this function on this screen, and then we'll be able to plot it onto our paper and see if we're doing the right thing or not. As with every function, we will graph it by plugging x multiplied with ln of x into the y1 on our screen. And before I click graph, which will give me something like this, I'll go and modify the window numbers to match what's on the page, what's on the paper in front of us. It seems that they want me to start at -1, somewhere around -1 on the x-axis, and stop somewhere around maybe 3 or 4. I'll take a liberty and say it's a 3. For the y minimum, I'm thinking maybe -1. That's kind of matching with what's on paper. And maybe 3 or 4 for the y max. I'll go with the 3 and we'll see what we have. So clicking graph, you can see that it's a nice smooth curve. And if I try to trace the value 1 divided by e, you'll see that that puts us directly at the minimum value. And notice how the x and y are basically the same with the exception of the minus sign. That's how I knew that the minimum value is -1 over e earlier. The other thing I want to point out here is that if I try to trace 0, you'll see that the calculator does not return a y coordinate. Remember, 0 is not part of the domain. That's why there's no y coordinate there. And the other interesting thing is that the function passes through the point where x is equal to 1. It's passing through the x-axis, so the y coordinate there is 0. You can trace a couple other points to be able to graph more accurately the curve that you're seeing on screen to the paper, but it doesn't have to be perfect. It just has to look so nice and smooth. So let's do that and see what it looks like. The crucial thing to remember is that this point over here at the origin is left as an open or hollow point, so make sure you don't solidify that point. Don't make sure you don't color it all the way in. It needs to stay hollow to indicate that the function is not touching the origin. It wants to be there, but it can't. It's not allowed to because of the domain. Also, I made it pass through the point 1, 0. We know this is the x-intercept, so if you want to point out that this is 1, 0, that would be great. And the x value of the minimum was 1 over e. The y value of the minimum was -1 over e. And I'm writing that this is a minimum value. And this is a pretty good graph. It doesn't have to be perfect. If we want a perfect graph, we will just look at the calculator. It just has to look kind of right. Now looking at example number 3, we have a function again, and this is a function that we saw in section 3.7. So if you don't remember, please go back and look at the video because I'll be skipping some details over here on how to find the derivative and the critical values because I already explained how those were found in a previous video. So watch that one to see how we got the critical values. But the question we have to answer is to find the open intervals on which the function is increasing and decreasing and the location of any relative extremas, and also finally sketch a graph of the function. So I want to point out first of all that the function here is a cubic function, meaning it has an x to the power of 3. It's a polynomial, and the domain of polynomials is all real numbers. This is the reason why you're seeing on the very first line of this problem that the domain is from -infinity to infinity. So we care about every number that appears. And as I said before, the derivative was found and factored in a previous video, so watch that to see how we get the critical values, -2 and 19 over 3. But once you find the numbers, the critical values, you are going to, again, perform the first derivative test, and this involves drawing this number line. And first of all, I'm going to write down the negative infinity and positive infinity, and I'm going to write down that this is the first derivative test, because like I mentioned, we will be doing this sort of test later on for the second derivative, and that will determine the concavity of the curve, so whether we're concave up or down, and whether we have inflection points or not. And we want to be able to distinguish whether we're working with the first derivative or second derivative, so that's the reason why I write those words on the side. The next thing you want to do is put the critical numbers on this line, and the order matters because we're starting with the smallest value and ending with the biggest value. So -2 is going to go first, and 19/3 is going to go somewhere after. And just roughly speaking, this is about 6.3. And so just for reference, we'll need to find some test values next. So we want to pick a number between -infinity and -2. Any number works as long as it's between those two values. So I'll go ahead and pick -10. Then I need a number between -2 and 6.3. So for the test value there, I'll choose the test value, I don't know, 0, I think is a good number to pick. And finally, something between 6.3 and infinity, I will go ahead and choose x equal to 10. Now, your test values could be different than mine, and I'll show you in a moment that it won't matter whether you plug -10, 0, or 10, or some other numbers. As long as the number you pick is between the numbers in the interval, then you'll be fine. So for example, with -10, I can plug it into the derivative, either on this line or on that line. Those are the places where I have a derivative. I'll go ahead and choose the factored version, and let's see what happens if I plug -10 into that. So I'm putting -10 into the derivative, and that will give me 3 times -10 with the -19, and it's multiplied by -10 plus 2. So 3 times -10 is going to be -30. -30 minus 19 is going to be -49, and what I care about is just that it's negative. And when I add the -10 with the plus 2, the answer is going to be -8. And again, the only thing I care about is that it's a negative sign. And a negative multiplied by the negative is going to result in a positive amount. So that's the reason why it doesn't matter whether you put in -10 or -8 or -25. The only thing that matters is a plus at the end. So because of the plus sign here, I'll go ahead and write down, record that finding underneath the line. I'll put that the answer was positive when I tested, and that indicates that the function f was increasing. So you can either write the words or write the little f with the arrow up to indicate that the function is increasing on this interval. We'll repeat again for the 0. So if I plug 0 into the derivative, then I would get 3 times 0 minus 19 multiplied with 0 plus 2. And so 3 times 0 is going to be 0. 0 minus 19 is going to be a negative amount at the end, so -19. But I don't care about the negative. I just care that it's negative. I don't care about the 19. So 0 plus 2 next is a positive answer. I don't care about the 2. And what I care about is that the product of a negative number and a positive number will be a negative solution. So because of this minus sign again, I will record in the middle interval that the result was negative, which implies that the function was decreasing on that interval. And finally, I'll test the 10. So testing the 10, we will get 3 times 10 minus 19 multiplied by 10 plus 2. And 3 times 10 is 30. 30 minus 19 is going to be some kind of positive number. And 10 plus 2 is going to be, again, like a 12. But again, who cares? It's just a positive number. And two positives multiplied by each other result in a positive answer. So we get a positive here that we will now record underneath. And because of that, the function f will increase again. Now remember, these testing values could be done with your calculator, they could be done in your head, they could be done anywhere on a scratch paper. I don't necessarily need to see them, so that's why I'm kind of relocating them here off to the side. But let's say you chose a different number. Let's say instead of choosing -10, you chose -20. Would it make any difference? So let's find out. F prime of -20. So I'm plugging -20 into the function derivative, f prime. I will get 3 times -20, 20 minus 19. and it's going to get multiplied by negative 20 plus 2. Will it make any difference? Well, let's find out. 3 times negative 20 is going to be negative 60, and minus 19 is going to be some kind of negative 79, so this is a negative answer so far. Negative 20 plus 2 is going to be negative 18, but again, who cares? It's just a negative amount, and when I multiply a negative with a negative, the answer is going to be positive, which is exactly what I said before. So that's the reason why it doesn't matter what the test value is. It just matters whether the answer at the end was positive or negative. So as long as you're choosing a number between the interval that you care about, it shouldn't make a difference. Now, what can we say about the function after we're doing all this work? So first of all, we know the increasing and intervals and decreasing intervals, and we also know the places where we have a maximum and minimum. For instance, right here, the function went up, then went down before and after that critical number. So that means that the number negative 2 has a maximum value because we had a bump before and then the function went down after. Similarly, the function went down, then up before and after 19 over 3, so that means that this guy has a minimum. So the function has a maximum and minimum, which is kind of special. Not every function does have both of them. But now let's go ahead and record everything. So we are going to say that f of x is increasing. And in this problem, we have two intervals on which the function is increasing, from negative infinity to negative 2, and also from 19 over 3 all the way to infinity. So how do we say that? We write the big old u sign in the middle. So this u is supposed to say that there are two intervals on which the function f of x is increasing, whereas the function f of x is decreasing only on one interval, and we're going to say it's decreasing on the interval from negative 2 to 19 over 3. So increasing on the interval, decreasing on this interval, and we have a maximum at the x value, which is negative 2, and we have a minimum at the value where x is 19 over 3. I'm not going to bother finding the y values of the max and the minimum because the question did not specifically ask for those. But if they do, I can just tell them how to, tell them roughly the answer by using my TI calculator. And speaking of which, let's see how we can plug this function into the TI calculator and see the maximum and minimum. So as with every problem, let's turn on our calculator and go to the y menu. And let's plug in the equation, which is x to the power of 3 minus 6.5 x squared minus 38x and plus the 240. So if I click on graph right now, I'm not going to see very much because the window is left over from the previous problem. So let's go ahead and reset it by clicking zoom 6. That will reset it to the standard window. This will always give us these values from negative 10 to 10 on both the x and the y axis. But again, we don't see the full graph here. And part of, building skills in this problem is figuring out the right window. You can cheat a little bit and look at the paper to decide, but, try to mess around with these window values. So maybe adjust the minimum x and the maximum x and so on until you get comfortable enough to where you can see the full graph. For now, though, I'm just going to use the values that are listed on the paper. So it seems that they want me to start at negative 6 and end somewhere around 9 or 10. And for the y minimum, it looks like they're going from about negative 50 maybe, all the way to maybe about 300. Maybe it's 350, but who cares? I'll just go with 300, and if it's wrong, I'll just come back and modify the window. Anyway, if I click graph, you can see the full cubic, and we are interested in finding if the answers were correct. We are expecting a maximum when x is equal to negative 2, and there you have it. The maximum happens at negative 2, and its value is actually 282. We're seeing that on the bottom of the screen right there on our calculator. The minimum happens when x is 19 over 3, so I'm going to trace that value. 19 over 3 was the minimum, and you can see the minimum value is negative 7.35. If you want to record that, be my guest. They did not specifically ask for it, so I'm not going to provide it. And if you care, we are passing the x-axis, we're passing the y-axis when x is equal to 0 and the y is 240. So that's another additional point that you can use while graphing while transferring this graph from the calculator to your paper. You can trace some random numbers and you'll get more points for more accuracy if you want. And once you're satisfied with how many points you've got, then just transfer the x and y coordinates to the page and draw the curve on the paper. So again, a reminder, it doesn't have to be perfect, it just has to look kind of right. And you can indicate the places where you have a maximum or minimum. So for example, in this problem, the maximum was at -2, the minimum was at 19/3. And that's pretty much all we need from you right now. So that's it. We're done with this problem. The last thing we will discuss in this section is the concept of concavity and how it relates to the second derivative and the function f of x. So in the definition, we're told that the function f of x is called concave up when the second derivative is greater than 0. And you can see in the image, that's where the function is concave up. So you can think of it like an U shape. So if water were to fall down from the sky, it would accumulate in this area. So that's what makes this area what we call concave up. Now, if the function is concave down, then we are told that the second derivative is negative. So you can think of it like an N shape for concave down and a U shape when the function is concave up. Another way of saying this is that the function f of x is concave up when the slopes are increasing, and the function is concave down when the slopes are decreasing, as you can see in the little graph that I have provided. Now, if a function has concavity up followed by concavity down, the point in the middle is what we call an inflection point. So inflection points happens when the concavity changes from being up in this area to being down on the other side, or vice versa. If we start with concave down, then we become concave up. The place where the transition happens from up to down is what we call the inflection point. And that's what's being told in the second definition. An inflection point is the place on the curve where the concavity changes. So let's look at example number 4, where we are told we have some kind of function f of x, and we need to find the intervals on which the function is concave up or down, and we need to locate the inflection points. So as we proceeded before, we're going to start by claiming or mentioning that this function here is a cubic. So its domain is going to be all the real numbers. So from -infinity to +infinity, we always do that first just to make sure. And in this case, everything is good to go because it's a cubic, it's a polynomial. The polynomials can accept any value of x. What we need next is to find the second derivative, but we'll begin with the function itself, and we'll have to find the first derivative and find the second derivative. So given this function f of x, the derivative f prime of x will be 3x squared minus 10x minus 8. But we are not interested in the first derivative anymore. Whenever the question has to do with concavity or inflection points, we need to be able to get the second derivative. So from this, we can proceed to get the second derivative f double prime, which will be 6x minus 10. So this is my second derivative, and what we need to do next is find the critical numbers as we did before. We're going to ask, where is the derivative equal to 0? Where is it undefined? It's basically the same questions that we've had to answer in the past, except we are working now with the second derivative. Okay, so for the second derivative to be equal to 0, I need 6x minus 10 to be equal to 0, which means that x has to be equal to 10 over 6, also known as 5 over 3 when I divide both sides by 2 on the numerator and the denominator. And for the second half of the problem, because I have a linear function 6x minus 10, the second derivative cannot be undefined, so there are no extra values that we get by doing anything on that part. So this is my second derivative, and we've located it, and we've located the critical numbers. So now what we need to do is draw the number line like we did in the previous problems. And this time, what we're going to do is label it as the second derivative test. So starting with -infinity all the way to +infinity, the only critical number that matters to me is 5 over 3. This is the only value that we found when we looked for the critical numbers. We'll need to test some value before and some value after. So pick a number from each of these intervals. As long as the number is between -infinity and 5/3, you'll be fine. So I'm going to pick, I don't know, -10. And I need a number between 5/3 and also infinity. So I'll go ahead and pick 10 in this case. So once I've decided the critical numbers, or sorry, the test values, I'm going to plug them into the second derivative in this problem. So plugging the -10 to the second derivative, I get f double prime of -10. Well, that's going to be 6 times -10 and another -10 on the side, which will give me -60 minus 10, and the total is going to be -70. And again, the only thing that matters to me is whether the answer was negative at the end or positive. In this case, it was negative. So I'm going to go ahead and record that the answer was negative. And because this is the second derivative we're working with, I'm going to have to say that the function f of x is concave down. So I'm going to put a double arrow pointing down, or you can write the words f of x is concave down. It's up to you. I feel like the symbol is a little bit faster, so that's why I'm doing that. Similarly, I'll need to run the test again, but for 10. So this time I'll go ahead and plug in 10 into the second derivative. And this will be 6 times 10 minus 10, which will be 60 minus 10. And the answer is going to be 50, which is positive. So the answer was positive, so I'll go ahead and record that underneath the interval. And because my answer was positive, and this is the second derivative, I'll have to write down or say that f is concave up, and I'll just do a double arrow pointing up for concave up. Since the concavity went from being down to being up, that means that the number in between is an inflection point. So at x equal 5/3, we have an inflection point. All right, so that always happens when your concavity changes. Sometimes there will be some problems where you have two pluses back to back or two minuses, and in which case the number in the middle, the critical value, is not going to be an inflection point, so you're just going to leave it alone and you're just not going to count it. As we mentioned before, this part with the testing is not necessarily required, so you can show it or not. You can do it on a scratch paper. It's up to you. It does not have to be visible. But the last thing I need to do is record everything in words, and that will be the end of the problem. So I'm going to say that f of x is concave up on the interval from 5/3 all the way to infinity, and we always use parentheses for all this. And the function is concave down on the other interval from -infinity all the way to 5/3. And we only have one single inflection point, so we're going to say that f of x has an inflection point at the place where x is equal to 5/3. If I am interested in finding the y-coordinate, by the way, we always find the y-coordinate by using the original function f of x. So you would take your 5/3 and you would plug it into this function f of x to get the y-coordinate of the inflection point. In this case, it doesn't seem like they want the y-coordinate, so we are pretty much done with this problem. So now we can combine all the information we have about concavity with information we have about extremas to sketch an accurate graph of the function that we're dealing with. And this process is called curve sketching. We'll be doing it for polynomials in this section. And again, in the next section, we'll be doing it for rational expressions, meaning fractions where we have x's in the numerator and the denominator. So in this problem, we're given that f of x is equal to 3x5 minus 5x cubed. So I want to write off the bat, say that the domain is from -infinity to +infinity. And how do I know this? I know this because this is a polynomial of degree 5, right? I'm seeing the 5 right there. There are no fractions with x on the denominator. There's no radicals. There's no logarithms. So there are no restrictions on my domain. So that's great. And remember, we need to find the domain first because it affects your maximas, minimas, inflection points, and sometimes it even affects whether you will have a vertical asymptote or not, or that's going to be later on in another section. But it's always a good habit to find the domain right off the bat, whether you're being asked to find it or not. Okay, so in part one of the problem, it's asking us to find the intervals on which the function f of x is increasing or decreasing, and to find the relative maximas or minimas. So to answer this question, we will be finding the derivative, the first derivative in this case, because we're interested in maximas, minimas, increasing, decreasing interval. then finding the critical numbers for it, and finding the places where the function is increasing, decreasing, and in return we will get the maximas. So, well, the fx here, it's going to be 3x5 minus 5x cubed. I'm going to begin by finding the first derivative. F prime of x in this case is going to be 15x to the power of 4 minus 15x squared. It's better to have it factored, so I'm going to continue. There are two terms in this problem, and I'm seeing that they both have 15 and they both have an x squared that is shared. So I'm going to factor out the GCF, which is the 15x squared, and that leaves me with x squared minus 1 from each of the terms. But even x squared minus 1 itself can be factored. It's actually a difference of squares, so I can rewrite this as 15x squared multiplied with x minus 1 multiplied by x plus 1. So first, basically what I did is I found the GCF. This is the GCF of the original problem. And then I did difference of squares to turn x squared minus 1 into the product of x minus 1 with x plus 1. Now that I have the derivative, I'm going to ask myself what makes it equal to 0 and what makes it undefined. Let's start with the first part where the f prime is equal to 0. This will happen when 15x squared multiplied by x minus 1 multiplied by x plus 1 will be equal to 0. So in other terms, either the 15x squared has to be 0, or the x minus 1 has to be 0, or the x plus 1 has to be equal to 0. This is because of the zero product property, which says if you have a product of multiple things equaling to 0, either the first one or the second one or the third one has to be 0 in the first place. Now, solving the first equation, for 15x squared to be equal to 0, you can divide both sides by 15 and you'll get that x squared has to be 0, which means x itself had to be 0. And that's the end of that part. For the second equation, I just need to move the 1 across, and I get that x is equal to 1. That's my second critical value or critical point. And finally, the last one is x equal to negative 1. You move the 1 across and it becomes negative 1, and that's the third critical value. And remember, we also need to know when is f prime of x undefined, and in this case, there are no places, there are no solutions to this kind of a problem because my derivative is this polynomial, and polynomials are defined everywhere, so there are no additional points beyond the first three that we have found already, negative 1, 1, and 0. So what I'm going to do next is draw the number line like we always do. This represents all the numbers in our domain, and in this problem, the domain starts from negative infinity. It stops at positive infinity, and we're doing the first derivative test to see maximas and minimas and increasing, decreasing intervals. We had 3 points in this problem that were critical values, and make sure you put them in order. So negative 1 will go first, 0 is in the middle, and finally 1 afterwards. And remember, this is the number line, so everything you put on this line has to be in order from smallest to largest. Once you've done this, we're going to need some test values. So I'm going to test some values in the first interval from negative infinity to negative 1. I'm going to pick negative 10 and test that value. From the middle interval, I'm going to test negative 0.5. That's a number between negative 1 and 0. From the third interval, between 0 and 1, I'll go ahead and pick 0.5 again. And finally, between 1 and infinity, I need to pick a number. I'm going to pick the number 10 to test that number. And where is all this testing happening? It's happening in the first derivative. So you can pick this or this version of the answer to plug into when you're doing your testing. For me, it seems like the easiest one is probably this last one. So I'm going to do all my testing into that equation. So starting with the negative 10, what would happen if I plugged in negative 10 into the derivative? Remember, the derivative was 15 times the x squared multiplied by the x minus 1 and then the x plus 1. Now, just so that we can make this process go a little bit faster, because we have to do this 4 times, I'm going to notice that no matter what I do, no matter what number I plug in, the 15x squared is always going to be positive. Whether I put -10 into it, or 0.5, or 0.5 negative, or positive, or 10, regardless of which number I plug in, because of the power 2, the x will always be squared, and so the x becomes positive no matter what. So we can, in theory, ignore this part right here because this will always be positive no matter what, and we could just look at the 2 other parentheses that will be left over. So in this problem, -10 minus 1 will be negative, and -10 plus 1 will be a negative again. So -10 minus 1 is -11, -10 plus 1 is -9, and the product of 2 negative things will become positive, and that's what I'm going to record for the first interval. Okay, so that's the end of the first interval. Let's try again with the -0.5 next. So I'm going to just use this notation and plug in -0.5 everywhere where I had an x previously. And as we said, I'm going to ignore the first part from now on, so I'm not going to worry about it because no matter what happens, no matter where I plug in, it's always going to be positive. Now, -0.5 minus 1 will be a -1.5, and -0.5 plus 1 will be a positive 0.5. And when you multiply those things, the answer will be negative, and that's what I'm going to write inside the second interval. So the second interval turns out to be negative. For the third interval, plug in 0.5, and what happens is we'll see 0.5 minus 1, which is a negative amount, and 0.5 plus 1, which is a positive amount. So we are again getting a negative solution there as well in that third interval. So I'm just going to record that. And finally, for 10, if I plug 10 into all the x's in my problem, what will happen into the first derivative? What will happen is I'll get 9 multiplied by 11. They're both positive. And when you multiply two positive numbers, the result will be still positive. And so that last interval is yet again positive. So remember, this testing can be done with a calculator. You don't have to do it by hand always, and you don't have to show it to me. So you can erase it at the end or just do it on a calculator. But the bottom line is the function f of x is increasing on the first interval, then it decreases on the second interval, then decreases again on the third interval, and finally increases at the end on the last interval. So what does that mean? Since we went increasing, then we went decreasing afterwards. The point in the middle is going to be a maximum value or a maximum point, right? We went up, then we went down before and after. And remember, this is the first derivative. That's why I'm saying increasing and maximum. Now, what about the second point? We went down before it, and then we went down even further after it. So it's neither a maximum nor a minimum. So this x equal to 0 does not have a maximum nor a minimum. It's just neither. So just ignore it, pretend like it was never there, and continue to the last point. So at 1, what's going on there? We went down before it, then we went up after it. So that creates a small valley, and the number is going to be at the bottom. So that will be what we call a minimum value. All right, so the last thing we need to do is record this in writing. So f of x is increasing, and just write down the intervals on which it's increasing. So it's increasing on the intervals from -infinity all the way to -1. And there's a second interval. So how do I say that there are 2 intervals? I put the little U sign that indicates that there are 2 intervals, and I'm about to write the second one, 1 comma infinity. And the function f of x is decreasing on the other interval from -1 all the way to 0, and also from 0 to 1. Also known as, if you like, sometimes we just write -1 to 1. Even though the graph technically was for a moment constant at 0, in certain textbooks they don't bother separating the intervals like this. They just kind of put it all together in 1. So just be paying attention to that, because sometimes in certain textbooks they will combine the 2 intervals, sometimes they don't. It just depends on the author's preference, really. And so those are the increasing, decreasing intervals. I'll just go ahead and add some words here saying that the f of x has a maximum at the point where x is equal to -1, and f of x has a minimum at the point where x is equal to 1. Now, if we want to know the y-coordinates for anything in this problem, we always go back to the original function. So if you want to know the y-coordinate when x is at the minimum or maximum, you will plug in the numbers 1 and -1 into this function, the regular f of x, to get the y-coordinate. And by the way, if you want to know the value of the maximum and minimum, I can tell you the values of each one of those. So the value of the maximum, putting -1 into the function f of x, you will see that the value is 2. And similarly, you will see a -2 when you plug in 1 into the original function, right? So test it out for yourself. Let's say you plug in 1 right there. It's going to be 3 times 1 to the power of 5 minus 5 times 1 to the power of 3. Now, 1 to any power doesn't matter, so we can just ignore the powers. And 3 times 1 is going to be 3, and 5 times 1 is going to be 5, and the total will be -2. Like we said, when you plug in 1, you get -2. And that's the value of the, in this case, it's the value of the point where I had a minimum. Okay, so that's the end of the first part, and so the answer is technically all of these words that I wrote at the end over here. Now, for part 2 of the problem, it's asking me to find the intervals on which the function f of x is concave up or down. So for that, I need to know the second derivative. And so keep in mind that we found the first derivative already. We actually had like 3 different ways of representing the first derivative. And we need to find the second derivative next. And the best option for finding the second derivative is to use the first way we had the derivative represented. This option here doesn't have any product rules or quotient rules or anything fancy. It's just 2 terms being subtracted, so we can use the basic differentiation rules to find the derivative. So I'm going to pick that option and transfer it down here. So my first derivative was 15 x to the power of 4 minus 15x squared, which implies that the second derivative is going to be, okay, so 15 is already there. I need to write 4x cubed for the derivative, and 15 times 4 will be basically 60 with the x cubed. There's again 15x squared, so there's a 15 already there, and the x squared's derivative will be 2x, so the product of that will be -30x. So that's my second derivative, and of course I need to know the critical numbers, so it's helpful to factor this as much as possible. So again, I'm going to use the GCF method. I'm seeing that there's 2 terms. They both have a 30 that I'm noticing, like 30 times 2 is 60 and 30 times 1 is 30. They also both have an x term that repeats. So this is my GCF. I'll just go ahead and write that down. GCF, that's the greatest common factor. And when I factor the greatest common factor, I'll be left with 2x squared minus 1 inside of the extra parentheses. And I'll stop here. This is not an easy or pretty difference of squares, so I'll just leave it alone. Okay, so next I need to know what makes the second derivative equal to 0. And so it will be equal to 0 when 30x multiplied by 2x squared minus 1 is equal to 0. Now, for this to be 0, the zero product property says either the 30x must have been 0 or the 2x squared minus 1 must have been 0, right? Remember this product, 30x times 2x squared, consists of 2 terms, so either the first term has to be 0 or the second term has to be 0, and that's according to the zero product property. Now, 30 times x will be 0 when x itself is 0. I think that's pretty obvious. 0 times 30 will be 30. Sorry, 0 times 30 will be 0. That's what I meant. And for the second equation, I need to move the 1, and I'll get to x squared equals to 1, which means x squared is really 1/2. This implies that x is either plus or minus the square root of 1/2. And personally, I don't have a problem with you leaving the answer like this. I know some instructors or some people prefer to have it rationalized, but for now, I'm just going to leave it like that and not bother too much. And so I am done with finding the second derivative. Oops. So once I found the second derivative, what I'll need to do is make the number line and test some values inside of each interval to determine the concavity. So here's my number line. This is all the numbers in my domain, and my domain starts at negative infinity and ends at positive infinity. Remember, this is the second derivative test, so I'll write f double prime test off to the side so we can remember that this is the second derivative that we're working with, not the first derivative. And the critical numbers that we found were 3 actually, so let's see, I'm going to put this as the square root of 1/2 with the minus sign, this is the 0, and this is the square root of 1/2. And so there's 4 intervals to test. Okay, so we'll need to test some kind of x value inside of each interval. And let's see, using our calculator, what the value of square root of 1/2 is, so we can kind of decide accurately which values to test. And so the square root of 1/2 is about 0.7. And remember, we have a negative value, so a negative 0.5 as well. Okay, so that means I can pick safely a negative 10 inside of the first interval. Since this guy here is roughly negative 0.7, I'm allowed to pick 0.5 with a minus sign there, and then 0.5 again with a positive sign there, and finally again I'll pick 10 for this last interval, because why not? Okay, there's nothing sacred about the 10 and the negative 10. I mean, they always show up in all my problems, but that's because it's easy for me to quickly multiply and add those numbers, so that's why I always end up choosing them. Anyway, now that we have the test values accounted for, we'll go ahead and plug them in to the second derivative, and we've got 2 options, either that one or that one. It's up to you. Just pick whatever you want and put it into any of the equations. So let's begin with testing the negative 10. So if I test negative 10, I'll go ahead and plug it actually into that. I think it'll be a little bit easier for me right now here. So it's going to be 30 times negative 10 multiplied by 2 with negative 10 squared minus 1. So by the way, negative 10 squared is going to be 100 positive. 2 times 100 is going to be 200, and 200 minus 1 will be 199. Well, ultimately, this is just a positive number. 30 times negative 10 is going to be a negative number, and when I multiply those two guys, negative with positive, the answer is going to be completely negative. So that means on the first interval, I'm going to have a minus sign. And because this is the second derivative, I'm going to say that the function is concave up on this interval. It's negative, so it's concave down on this interval. Okay, I apologize. I said up, but I meant down. Since we're writing 10s, let's do the other 10. So I'm just going to ignore the negative and put a plus instead of the negative, and let's see what happens. So 10 squared is going to be 100 again. 200 minus 1 is going to be 199, which is positive anyway. And 30 times 10 is going to be positive. 2 positives get multiplied. The answer is going to be completely positive. So I'm going to write that down at the end over here, say positive, and record that the function is concave up on this interval because the second derivative was positive. Okay, so it remains to test what's going on at 0.5 and negative 0.5. So let's go ahead and do that next. I'll start with 0.5 first. Okay, so I'm going to replace all the x's with 0.5, and let's see what happens. So 0.5 squared is going to be some 0.25. Multiplied by 2 is going to be 0.5. With a minus 1, it's going to be some kind of a negative number. And 30 multiplied by 0.5 is going to be 15, which is some kind of positive number. And when you multiply those two things, you will end up with a negative amount. So the 0.5 gives me a minus negative solution. And similarly, you can test the last interval and you'll determine that the derivative here was going to be a positive amount at the end. Okay, so you can use your calculator to do a lot of this testing. So for instance, if I want to use my calculator to do the testing, here's what it would look like. I would plug in the 30, then let's say you're testing the negative 10, you would put in the negative 10 into the parentheses, then you're supposed to have the 2 times the negative 10. So again, make sure you're using plenty of parentheses. And finally, minus 1. And as you can see, when we tested the negative 10, the answer we said was going to be negative, and specifically it's negative 59,000. roughly 700. But it doesn't matter what you picked, like as long as it was between negative infinity and negative square root of 1/2, it would have worked. For 10, you could just basically do this, recall the previous entry, and just go back and delete the minus sign and delete the other minus sign on the negative 10. And that's your test for the positive 10. And you'll see, again, it's positive, just like we said on paper. For 0.5, you'll do something similar. So let's start with negative 0.5 since I didn't do that by hand. So I'm putting the 30 times negative 0.5, and then I'm going to need to multiply it with 2 by negative 0.5 squared minus 1. And let's see, there's the answer positive, and we said earlier that we expected a positive there as well. In any case, this means that the function is concave up on this interval, and the function is concave down on that interval. So we went down, up again. So cool. What does that mean? Well, let's first record all these findings. So the function f of x is concave up on the interval from negative square root of 1/2 all the way to 0. And there's a second interval on which the function is concave up, so I'm going to have to put the union sign and then 1/2 comma infinity. So we're concave up on basically those two intervals, but we are concave down on the other two intervals, so we're going to write that next. So f of x is concave down, I'll write it in capital letters, down on the intervals from negative infinity to negative square root of 1/2. And again, make sure whenever you're writing any of these, always use parentheses. It's always an open interval. And then it's also concave down from 0 to the square root of 1/2. Okay, so let's look at the next part. The next part is asking us to find the location of the inflection points. So we already did all the work. As a matter of fact, I'm just going to bring back that test that we did on the first page. And I don't know why they decided to separate it here, or why they decided to separate it and should have kept it together, but oh well. Let's see. Well, I was concave down, then I was concave up. And so whenever the concavity switches, the point in the middle is going to be known as an inflection point. So this is an inflection point. I'm going to just write INF for inflection. I'll capitalize it. And so again, we were concave up between negative square root of 1/2 and 0. Then we went concave down from 0 to square root of 1/2. So what does that mean? Again, that means that we have another inflection point at the point where x is equal to 0. And finally, we were down concavity. Then we became up, transitioning from the third to the fourth interval. So that means, again, we have an inflection point at this location where x is equal to the square root of 1/2. And again, if you want to find the y-coordinates of any of these points, you will plug them into the original function. And remember, the original function is the f of x. And so in this problem, the f of x, remember, used to be on the first page 3x5 minus 5x cubed. So if you want to know the y-coordinate of this point, you will plug this value that you have into this, and you will get the y-coordinate. Similarly, same thing you do here. So for example, this one is really easy because if I plug in 0 into all the x's, I'm just going to get 0 for the y-coordinate. So the x is 0 and the y is 0, so we're passing through the origin there. And if you're interested, we can determine these values, or we can look them up in the calculator in a couple of seconds, in a couple of minutes when we do this with the calculator. But if you want to know the exact values, this will be 7 divided by 4 square root of 2. And this is negative 7 divided by 4 square root of 2, in case you want to know the exact values. But anyway, now that we have all this done, they want us to completely sketch the graph of the whole function. So let's start by graphing it this time and then figuring out whether we did it right or not using the calculator later on. So what we're going to do is recall everything we did in the previous parts of this problem. So for example, at some point in time, we said that the function was increasing and decreasing. And if you recall, we said that the function was increasing on the first interval all the way up to -1. Then it was again increasing on the interval from 1 to infinity. So on this graph, the function should be increasing and it should be increasing, at least on these intervals. We also said that the function was decreasing on this interval from -1 to 0, and again from 0 to 1. So from this part to this part, we should expect a graph that kind of goes downhill. And I know that this is a polynomial graph, right? This function f of x is a polynomial, so I'm expecting a very nice and smooth graph. So if I were to guess, I would guess that the graph should look something like this. It goes up nice and smooth, it comes back down nice and smooth, and then it goes back up nice and smooth again. So that's kind of what I'm expecting on those intervals. I know that at -1, I had some kind of a maximum, I believe, because I was increasing then decreasing. So I know it's somewhere high. I did not check exactly the y-coordinate. We didn't do it. But we know we should be at a highest point over here. And that kind of makes sense because we're going up, then we should go down. So at -1, roughly, we're going to be somewhere along this line at a very high point. And the same thing happens again when we get to 1. At 1 itself, we know we're at some kind of low point. So maybe it's -1, maybe it's -2, maybe it's somewhere in the middle between them. We don't know, but somewhere around this line, there's a point where we'll be at the minimum. So far, the graph should go up to the maximum, should come back down to the minimum, and it should kind of go back up afterwards. And we did not test out exactly the y-coordinates of the maximum and minimum. So for now, we don't know how high it's going to be, but we're just going to guess that this is what the graph should look like. And keep in mind that we also had some kind of work that we did about concavity and inflection points. And we said that there's an inflection point there at 0. That was one of the inflection points, if I believe, right? We said it over here. So we're expecting an inflection point there at that location. And also another one around -√1/2. We're expecting another inflection point as well at that location. So that √1/2, I'm not sure exactly what the value is, I forgot, but let's go ahead and test it out with a calculator. Let's see, what was the √1/2 equal to? √1/2 was equal to 0.7. So I'm expecting some kind of inflection point around 0.7 and around -0.7. So those are somewhere here, and somewhere 0.7 will be somewhere there. So I'm expecting the graph to be concave down on this section. Then I'm expecting it to be concave up on that part. Then down again on this part. I'm exaggerating how concave up or down it is, and then again concave up on that part. And like I said, I'm super exaggerating how concave up and down it is. When we actually graph it, you'll see it's barely noticeable that it's concave up and down. I mean, this part is going to be very obvious. This part over here at the end will be very obvious, but the ones in the middle are not going to be quite as exaggerated as I'm making them seem over here. But anyway, the general idea is I think that the graph should look like this. And again, it's kind of debatable how high and how low those curves are going to be, and it doesn't necessarily have to be super symmetrical like I'm making it seem. But I also know that one of the inflection points is at 0, 0, so I know for sure we'll be passing through the origin. So the graph that I'm expecting is something that looks like this, and we can confirm if I have the general idea correct or not using the calculator. And we'll also have to modify exactly where it's passing through on the x-axis. We know it's passing through the origin, but there's other points where it's going to cross through the x-axis. Also, we will determine how high and how low to make the graph. So we'll do that by using the calculator. And as usual, you're going to need to put in your equation to y1, and once you've plugged in the equation, you can click on zoom and just go to the standard zoom as usual, and you'll see the graph. But I mean, this is not exactly what we want on paper. On paper, they decided they want some specific values between -2 and 2 on the x-axis. So let's go to the window and modify our window a little bit to go from -2 all the way to +2 on the x-axis. And as you can see already, by clicking graph, the graph significantly improved. But we also want to modify the y-coordinates. On paper, it seems like they're going from -4 on the y minimum and all the way up to 4. So let's go ahead and do that. And so clicking graph again, you can see the graph now looks beautiful, and we can trace as many points as we want and see what's going on and kind of estimate everything. And so let's first start by tracing the 0, 0. This is an inflection point. Remember, the first derivative resulted in a 0 as a critical value, but it was neither a maximum or minimum. So as we can see right there, it's not a maximum, it's not a minimum, so that confirms our findings. We had something at -1 that we called a maximum, and you can see it's a high point at that location. It's not the highest point of the whole curve, that's why I didn't say global maximum, I just said maximum. And we also had something similar going on when x was equal to 1. We had a minimum there, and again, it's not a global minimum, it's just a minimum. And we had something cool going on around the square root of 1/2, which we said is roughly 0.7. So let's go ahead and trace, actually, the square root of 1/2 and see where that puts us. We had basically said that there's going to be an inflection point here. And there you go. You can see before and after that point, slightly before and slightly after, the curve looks like an N a little bit before, and it looks like a U, the letter U afterwards. So that's a place where the concavity changes. Another place was the 0. Before it, the function was concave up. After it, the function was concave down. And the final inflection point was the negative square root of 1/2. And so again, you can see that the function is concave down before this point and concave up after this point. And obviously, a benefit of using the calculator and tracing these values is we get the y-coordinates for free. So like, for example, I'm seeing that the y-coordinate for the inflection point is 1.23. And for the maximum, for example, the y-coordinate is 2. So we can use all that to our advantage, but generally speaking, our graph was sort of accurate, but we'll just have to clean it up a little bit and make it look a lot better than what it does right now. So let's go ahead and erase all this stuff. And again, I want to point out that we were increasing on this interval, and we're supposed to be increasing on this interval, and we're decreasing on that interval. And we're concave up until we get, we're concave down up until we get to negative 0.7. And something again happens at 0.7. And something happens at 0, 0. So we are supposed to be concave down here, then concave up here, then concave down here, then concave up here. So I'm trying to separate the colors so you can see where the concavity changes and also see where the graph itself has increasing, decreasing intervals. So the concavity is going to change at those intervals, and it's going to be a different concavity than this pink and this other pink interval. And we know that at the maximum, we're going to be at -1, 2, so we're going to try to make it go up to here. Similarly, the minimum is at 1, -2, and we can just verify real quick with the calculator. So when I plug in 1 into my calculator, you'll see that the y-coordinate is -2, so that confirms the minimum value. Where am I crossing the x-axis? We can just kind of eyeball it right there by going around here. You can see it's between 1.27 and 1.3. So, somewhere around there, maybe 1.25. Let's trace 1.25. And you'll see it's not exactly right. What about 1.26? Not exactly right. 1.28. Let's see what that does. 28. That's 1.28 is still a little bit lower. 1.3 is a little bit higher. So somewhere around 1.29 maybe, that's going to be our estimate. We can do this a little bit better by clicking second and then trace, and then finding the 0 of the function, option number 2. We've done this before, but as a review, you just click enter there. It's going to ask you for the left bound, so you go to the left side of the intersection with the x-axis, and then it's going to ask for the right point, so you're going to go to the right side of the intersection, and you just click enter. And now you see it says 1.2909944, and the y-coordinate is basically 0. So we know it's roughly speaking 1.3. So if you are interested in making it as accurate as possible, you're going to be trying to pass through 1.3. So maybe that's a little bit more to the right since 1.5 is there. And similarly on the other side, because of symmetry, is going to pass through the x-axis here. So my graph should look something like this. It's concave down on this interval, and it's concave down up until I get to the point where x is 0.7. Then I'm going to be concave up. Then I'm going to be concave down up until the point I get to the 0.7, so somewhere around 1.23. And then I'm going to be concave up again And keep in mind that we are increasing on this interval, then decreasing on this whole interval, decreasing again on this whole interval, and increasing again on that whole interval. So that's kind of what the graph should look like ultimately when you're finished. And so again, it doesn't have to be super, super accurate, just has to kind of look like what's on the screen in front of you on your TI calculator, and you can trace as many points as you want and take your time to make it as beautiful as you can.